You already know some examples of metric spaces, in some previous math classes, like, for example, on the real number line, we have two real numbers, x and y on it. And then, what is the metric? Metric means distance. Then what is the metric or distance between those two numbers, x and y, on the real number line? Distance, d, or metric d, between two real numbers, x and y, on the real number line was usually defined by what? Absolute value of their difference, right? That was a kind of distance between, or metric between the two real numbers on the real number line r. Or, how about in the more general Euclidean space, two-dimensional, three-dimensional Euclidean spaces? For example, in the two-dimensional Euclidean space, we have two points. Two points x and y in the two-dimensional Euclidean space. And then what is the d metric between those 2 points in the two-dimensional Euclidean space? That's precisely the metric, the distance between those 2 points in the xy coordinate system. And that's how do we evaluate or compute the precise metric or distance between the 2 points in the two-dimensional Euclidean space. That's square sum of the difference between the coordinates and take the whole square root of it. Right? That was how we compute the metric or the distance between the 2 points in the two-dimensional Euclidean space. Okay? So you already have examples of what? Metric spaces. Okay? In the basic algebra class, you have studied long time ago. Yeah, by the way, then the metric D is a two-variable real-valued function, right? The metric D is a two-variable real-valued function. Real-valued function. More precisely, the metric D is a function from what? From the Cartesian product of the set X with itself to the non-negative real number, right? Non-negative real number. Yeah, on this first metric example, our set X was the real number, the whole real number line, or on the second example, the set X was what? For two-dimensional Euclidean space, etc. Right? Etc. So by the way, the metric, the distance function, that's a distance function, which is a function from the Cartesian product of any some set by itself to the non-negative real number, Yeah. Okay, then let's describe the general definition of the metric space then. Okay? Let's describe the general definition of the metric space based on those very specific basic examples. Definition. A metric space XD, where X is a set and D is a metric function, is a set X together with a function, more precisely distance function, D, which is a function from the Cartesian product of the set X with itself to the non-negative real number. Okay, non-negative real number, satisfying the following three different properties, such that, first of all, distance between the two elements x and y is equal to 0 is equivalent to what? If the distance between two elements is 0, then that must be equivalently what? Then the two elements x and y must be identical, right? Equivalently. And secondly, that's a kind of what? Commutative property. Yeah, distance between two elements x and y must be same as distance between the other way around, right? Y and x. For all elements x and y in the set X. And the last property is about the triangle inequality. Okay? The triangle inequality. Distance between two elements x and z must be less than or equal to distance between the other two elements x and y plus distance between the other two elements y and z. For all x, y, and z elements in the set X. That's the formal definition of a metric space. Okay? Metric space. We must have a set X, and we must have a function D, defined from the Cartesian product of the set X, Y itself to the non-negative real number. And the metric function D must satisfy those three conditions, rigorous conditions, mathematical conditions. Which makes sense, right? Yeah, distance between, the metric between two elements is nothing. There is no distance between two elements. Then what should be happened? Equivalently. Those two elements must be identical, right? Equivalently. And of course, the distance function must be commutative, right? Distance from here to there must be same as what? Distance from there to here, right? That makes sense. And the last one is what? A kind of triangle inequality. You are very much familiar with in the usual what? Absolute metric, right? You have studied in the previous algebra classes. Yeah. Those are two examples about metric spaces. Right? We already have two examples of metric spaces. So let's let our set X be the whole, let's go back to this very first example. Let's let our set X be the whole real number line R, and let's let the metric function D between X and Y, the two real numbers X and Y, be what? Absolute value of X minus Y. Okay? Absolute value of the difference between the two real numbers. And then you can easily check, okay, this metric function D, this distance function D satisfies all those three rigorous conditions. Okay? Yeah. You can easily check it out. Okay? Absolute value of X minus Y is equal to 0, then must be equivalently what? Two elements X and Y must be identical real numbers. And absolute value of X minus Y must be equal to what? Absolute value of Y minus X. Of course, that's true. And you also know the famous triangle inequalities for absolute values. Right? Yeah. So the whole real number line R with usual absolute value function is what? Is a kind of example of a metric space. The usual metric, we say that that's a usual metric on the whole real number line R. On the whole real number line R. How about the second example? In the two-dimensional Euclidean space, let's let the set X be the whole two-dimensional Euclidean space, and on that whole two-dimensional Euclidean space, we have this metric function D defined by this here. More precisely, that's sum of, what I mean is square root of sum of squares of difference between coordinates, where I is from 1 to n, more precisely. Yeah, in this two-dimensional, n is 2, so I is from 1 to 2, something like that. And that's another example of metric space. How about in Rn space? more general are an n-dimensional Euclidean space with user metric you have already experienced on. That's what we want to focus on for, on the next, next step here. Let's see. On the n-dimensional Euclidean space, on the n-dimensional Euclidean space, which is the set of all n-dimensional vectors. Right? N-dimensional Euclidean space. X is the n-dimensional Euclidean space, which is the collection of all n-dimensional vectors. So let's let the function d between two elements x and y on the n-dimensional space be defined by square root of sum of squares of difference between coordinates. Where both x and y are two n-dimensional vectors. If n is equal to 1, it goes back to the very first example with absolute value metric on the whole real number line, one-dimensional, one real number line. If n is 2 here, then that goes back to the second example on the whole two-dimensional Euclidean space with this user metric we have defined there. So in general, on the n-dimensional Euclidean space, the n-dimensional Euclidean space with this D metric defined function is a metric space. That's a metric space. Which means this D metric function satisfies all those three rigorous conditions. We can easily prove the first and the second one, but it's very challenging to prove the last one here, triangle inequality. We will spend some time to prove, justify, okay, all those three conditions are satisfied for this n-dimensional Euclidean space with this D metric defined. Yeah. So what I mean is we claim this setting over here is a metric space. Okay? This D distance function is a metric on the set which is the n-dimensional Euclidean space. That's what we want to justify. We want to spend some time to justify. Yeah. How can we easily prove the first condition over here? Okay, so let's let both x and y be two different n-dimensional vectors in Rn. Then, what do you mean by D function values of x and y is equal to 0 then? That's equivalently, by the definition of D function, if you apply the definition of the D function there, that means square roots of sum of squares of difference between coordinates must be 0. Then that's equivalently what? If you square the both sides, then the square root is gone. So that's equivalently sum of squares of difference between coordinates must be 0 equivalently. Then what should be happen equivalently? Actually, each term inside the summation is non-negative, right? So the sum of non-negative numbers must be 0, then what must be happen? Sum of non-negative numbers. Each term inside is non-negative, but their sums is what? 0. Then what must be happened to each term inside? There is no other choice. Each term inside must be 0. So each term inside the summation must be 0. Then equivalently what then? Take the square roots back to the both sides, and then what? Each difference between each coordinate must be 0. Then equivalently what? Each coordinate must be identical. Then finally equivalently what then? Each coordinate for x and y vectors is identical, so what? Then we must conclude two n-dimensional vectors must be identical. So the metric values between x and y is equal to 0 is equivalent to what? Two n-dimensional vectors x and y are identical, which proves the first condition here. The proof for the second condition is very much straightforward, right? So again, let's let x and y be two n-dimensional vectors. Then, of course, the D-metric function is commutative, right? Yeah. That's a very trivial proof. The distance between x and y is same as, by the definition of D function, that's half power square root of sum of squares of difference between coordinates of the vectors, which must be equal to square root of sum of squares of difference. You can switch the order of subtraction here because of the square, right? That's what's happened because of the squaring. There is no difference for. Then that's exactly the same as what? D function between y and x by the definition of D function there, right? So that's true for all n-dimensional vectors x and y. So the second condition is easily, trivially proved, right? So the first and the second conditions are easily proved, but how about the last one, which is more challenging? To prove the last one, the third condition here, we need some lemma, which is so-called Cauchy-Schwarz inequality. I don't know if you have heard about it. For the proof of the last condition for the metric space there, for this, the example for the n-dimensional Euclidean space, we need some lemma which is called Cauchy-Schwarz inequality. Again, Cauchy, Cauchy-Schwarz inequality. Which says the following. The Cauchy-Schwarz inequality says, for any real numbers a1, a2 up to an, and b1, b2 up to bn, sum of product of each component is less than or equal to square root of sum of squares of the component of the first vector times another square root of sum of squares of the component of the second vector. This is so-called Cauchy-Schwarz inequality. Okay, Cauchy-Schwarz inequality. What is the geometrical meaning of this Cauchy-Schwarz inequality? What do you mean by the left-hand side, which is the sum of the product of the components of those two n-dimensional vectors, right? That's exactly what. The left-hand side is exactly what? The dot product of the two vectors A and B. Dot product, you remember the dot product you have studied in linear algebra, right? So dot product. Let's let A be the first n-dimensional vector, a sub 1, a sub 2 up to a sub n, and let's let B be the another n-dimensional vector, which is b sub 1, b sub 2 up to b sub n. Then the left-hand side over here in this inequality is exactly what? The dot product of the two vectors A and B. Okay, dot product of the two vectors A and B. That's what the left-hand side in this inequality is about, which must be less than or equal to. What happened? What do you mean by the right-hand side expression? Square root of sum of squares of each component of the first vector. What does that stand for geometrically? Norm of the first vector A. You understand this notation, norm of A. Norm. That's exactly what? The distance between the origin 0 and the vector A itself in the n-dimensional space. And what do you mean by the second factor over here? That's by the same way, that's the norm of the second vector B. Okay? Norm of the second vector B in the n-dimensional Euclidean space. So that's the Cauchy-Schwarz inequality, which says that what? The dot product of the two vectors is less than or equal to what? The product of norms of each vector. That's what that means. So this lemma is needed to prove the third condition. Okay, third condition. Okay, third condition for the metric space here. Okay, yeah. Well, let's see. Okay. I hope this space is enough to finish the proof of that Cauchy-Schwarz inequality lemma thing. Okay. Yeah. How do we prove this lemma? How do we prove this lemma? Cauchy-Schwarz inequality. And then this lemma will be used to finish the proof of the third condition for the metric space of this example. Afterwards, that for the proof of this Cauchy-Schwarz inequality lemma, let's take another parameter lambda for any lambda parameter. What happens to sum of squares of a sub I minus the parameter lambda times b sub I? Of course, that must be what? Non-negative because of the squaring there. And if we expand this out by FOIL, then what is happening? That's what's happened if you do FOIL. And then let's split it out. Let's split the summation. That's what's happened. At this point, let's define some specific lambda. What is our choice of the specific lambda for our goal to prove this Cauchy-Schwarz inequality? So let's let lambda be that specific number, which is the ratio of, let me be quite much careful over here. Ratio of sum of the product of each component of the two vectors A and B, and sum of squares of the component of the second vector B. Yeah, let's choose this specific lambda value and plug that in here. Okay, plug that in here, then let's see what's happened. Well, over here, then our choice of lambda may have some trouble. What trouble can we have to use this kind of choice of lambda value?
If all the components of B are like 0,
yes, then the bottom number is 0. If all the components of the second vectors B are 0, then what is happened? This result is trivially true, right? If every BI is a 0, then what is happened to the left-hand side? 0, right? And what happens to the right-hand side? Another 0. So that inequality is trivially true, so we don't have to worry about that case, right? Yeah, we don't have to worry about that case. Yeah, that's what, yeah. Let's see, okay. So if all BI is 0, then the result is trivial. Okay, the result is trivial. So we assume, okay, some BIs are non-zero, which means we may assume the bottom portion of that choice of lambda is some positive number. That's what we may assume here. So we may assume the bottom portion, sum of BI squares, is positive, some positive number. And then let's plug our choice of lambda here, then what is happened? Then you can easily see we have exactly what? The result of the Cauchy-Schwarz inequality by simple computation. You can easily check it out. So I need some space. So let's plug this choice of lambda in here and there, which must be greater than or equal to 0. Then what is happening? Sum of a sub I squared, okay, minus twice of our choice of lambda is sum of a sub I times b sub I, and there is another sum of a sub I times b sub I, so we must have square of sum of a sub I times b sub I over sum of b sub I squared times that's the second term over here. I believe that's all for the second term over here. Yeah, plus, how about the last term? Square of lambda is what? Square of sum of product of AI and BI over let me see. Yeah, square of the bottom square of the bottom times another sum of square of bi's, and then one sum of squares of bi are cancelled out. That's good. And then we can combine those two terms together. If we combine those two terms together, minus 2 plus 1 makes just minus 1, and the last term is disappeared. Yeah, that's what's happened in our final computation. When we plug our choice of lambda in here and there, and then simplify, then that's what's happened. That's what's happened. And then finally, move this term to the other side and multiply both sides by sum of b sub I squared to have our final result there. Which implies what we have desired. And then that implies, yeah. Less than or equal to that's what's happened. And then finally take the square root to the both sides. If we take the square root to the both sides, then we have exactly what we have desired there. Yeah. So that's the proof of Cauchy-Schwarz inequality. Any questions on the proof of the Cauchy-Schwarz inequality? Then how does that Cauchy-Schwarz inequality prove the last condition for the metric space here? Let me erase here then to get some space here. Okay. Then how do we prove the result of the Cauchy? How do we prove the last condition over here for the metric space using the Cauchy-Schwarz inequality down there, lemma? Well, actually we want to show that. We wanted to show that distance between x and z is less than or equal to sum of distance between x and y and distance between y and z. Equivalently, we wanted to show that how do we write it out? How do we write out? We wanted to show that sum of square of x of I minus z sub I is less than or equal to what I mean is square root. We want to show that square root of sum of square of difference between coordinates of x and z is less than or equal to square root of sum of difference between xi and yi plus another square root of sum of square of y sub I and z sub I. That's what we wanted to show equivalently. So let's let a sub I be x of I minus y sub I. Let's let a sub I be x of I minus y sub I. And let's let b sub I be y sub I minus z sub I. Then automatically, if we combine them together, x sub I minus z sub I will be re-expressed by the sum of a sub i's and b sub i's. If we can easily check it out. So let's do this substitution to simplify our expression. So then equivalently, we wanted to show that what? Square root of sum of squares of a sub I plus b sub I, which is the left-hand side, is less than or equal to square root of sum of a sub I squared plus square root of sum of b sub I squared. Okay? That's what we wanted to show. Expand it out. Yeah, first of all, square the both sides and expand it out. The simple algebra. Okay? Square the both sides and then expand it out. Then what has happened? So equivalently, we wanted to show that if we square the both sides and expand it out, then what is happened? Let me write down the result of the computation. If we square the both sides and expand it out, then what's happened is that then we wanted to show that sum of a sub I squared plus twice of sum of a sub I times b sub I plus sum of b sub I squared is less than or equal to sum of a sub I squared plus twice of square root of sum of a sub I squared times another square root of sum of b sub I squared plus sum of b sub I squared equivalently. So we wanted to show this inequality. If we show this inequality and then let's go backwards, and then that equivalently implies what? Our original inequality we wanted to prove, okay? Which is the last condition for the metric space. But this inequality is automatically proved by what? The Cauchy-Schwarz inequality result. You can easily see that. Because what? Compare the left and the right hand sides. And then what? Sum of a sub I squares are cancelled out from both sides. And then sum of b sub I squares are also cancelled out from both sides. And what's only left over? Cancel 2 from both sides of the equation. Then what's only left over on both sides? Which we wanted to show. We wanted to show that then what's left over. We wanted to show what's left over, right? The left over is what? Sum of a sub I times b sub I. Which is the only thing left over on the left hand side is less than or equal to. How about the right hand side? Square root. Square root of sum of a sub I squared times another square root of sum of b sub I squared. So we wanted to show this inequality, which is equivalently what? Our original result we want to prove. But this is true. This is clearly true by the Cauchy-Schwarz inequality. That's exactly what the Cauchy-Schwarz inequality, which we have already proved, right? But this was already proved. Proved by the Cauchy-Schwarz inequality result here. That's exactly the Cauchy-Schwarz inequality. What I mean is, So we are done then. Yeah. So the third condition for the matrix space of this example was proved. So then, we conclude that on the n-dimensional Euclidean space, this D function makes a matrix space. Any questions or any comments on this? Let me describe an example of a non-Euclidean matrix space you may be pretty much interested in. Let's let the set X be the collection of all continuous functions defined on a closed bounded interval from A to B on the real number line R. Let's let the set X be the collection set of all continuous real valued functions defined on a closed bounded interval from A to B on the real number line R. We have focused a lot in real analysis, right? The last year. Let's let the function D between the two functions f and g be defined by intuitively what is the right definition of the metric D between the two continuous functions f and g defined on the closed bounded interval from A to B on the real number line R. Here is the domain interval from A to B on the real number line R, and here is the first function f. First continuous function f defined on the closed bounded interval domain from A to B, and there's another second function g, another continuous function g defined on the same domain interval from A to B. There are two functions two continuous functions f and g in the set X defined on the closed bounded interval from A to B. And then intuitively, what is your choice of the distance function, metric function between those two functions, f and g? Area between. You can compute what? Pointwise distance, right? Yeah, depending on your choice of x, right? We have the distance between f of x and g of x. If we choose different x value in the domain, then we have a different f of x minus g of x, right? So we have a bunch of distances, pointwise distances, depending on our choice of x. And then choose the supremum, maximum of those distance values, right? So let's take the maximum, or you may say supremum. Both are the same, because both are the same. Okay, maximum or supremum. We usually use the term supremum. Supremum of difference between f of x and g of x, where x is on the domain interval from A to B. There are a bunch of pointwise distances, right, between f and g functions, and then, among all those pointwise distances, take their supremum, maximum value. So geometrically, where is that distance, supremum value of pointwise distances on this picture here? I believe this is the value, right, on the picture. This is the value. What is the largest maximum pointwise distance value between the two functions f and g? Here it is, right? That's this value there, supremum, the maximum of pointwise distances. Yeah. Then we want to claim that this set X with this D function D is a metric space. That's what we want to claim. Which means this D function defined on the Cartesian product of this set X with itself satisfies all those three rigorous conditions. Again, the proofs of the first two conditions are very trivial and easy for you, but the proof of the last condition, the triangle inequality condition, will be a little bit more challenging. Yeah, by the way, this D distance function makes the metric space on that set X, which is the collection of all continuous functions, real valued continuous functions defined on the domain interval from A to B here, closed bounded interval from A to B there. That makes a metric space as well. That's a kind of an example of a non-Euclidean metric space. Non-Euclidean metric space. Non-Euclidean metric space. Let me show you another example of non-Euclidean metric space. How about distance between two sequences? We have two sequences, real valued sequences. Then how do you define the distance between the two sequences on the real number line? That's another example of non-Euclidean metric space. Well, so let's by the way, let me introduce the notation of this set X over here in this example. This cap X set is the collection of all continuous functions defined on this closed bounded interval from A to B. So its notation is capital C at the domain interval from A to B. That's the standard notation of this collection of all continuous functions defined on the closed bounded interval from A to B. Okay, we use. And another non-Euclidean metric space is the following. Let's let capital X be the collection of all real valued sequences. Real valued sequences. The collection of all real valued sequences where each x of I is on the real number line, and one more condition, which is sum of the squares of the terms is finite, which may not be true. That's infinite sum, right? Infinite sum of squares of the terms of the sequence is finite number, which may not be true in many other cases, right? For example, if the sequence is 1, 2, 3, 4, set of all natural numbers, right? Their square sum is infinite, not finite, right? So this kind of example, this example is not on this set X, for example. So this capital X is the set of collection of all real valued sequences such that the square sum of the terms is finite. And then let me introduce this, kind of standard notation of this set X. We usually use little l square at set of all natural numbers like this. That's the standard notation of this set X, which is a collection of all real valued sequences whose square sums, okay, such that the square sums of terms is finite. Sums are finite. Yeah. And then, what is the definition of D metric on this set X? Let's let D xy are two sequences on this set X. let's define the function between two sequences x and y in this set be square root of sum of squares of distance, the difference between the components. That's another infinite sum, right? Infinite sum. Square root of sum of squares of the difference between terms of the sequence where I is from 1 to infinity, right? Yeah. Where both x and y are two sequences in this set X. Then we want to claim that this set X and the distance function D makes a metric space. Which means this function D satisfies all those three conditions of the definition of the metric space. That's another example of non-Euclidean metric space. Non-Euclidean metric space. So what I want to point out at this point is that our set X does not have to be just a Euclidean space. We are very much familiar with. And our function D does not have to be just a user metric, distance metric happened in the Euclidean space we are very much familiar with. It doesn't have to be. Capital X may be any set. And capital D, the D function may be any function satisfying those three conditions. Then that makes a metric space. Then that defines the distance between two elements in the set. In the abstract sense. So we will spend some time to justify the prove that those two examples are non-Euclidean metric spaces next time. Any questions for today? After we define the metric space, and then you remember the real analysis. On the real number line we have absolute value of two numbers, something like this, right? Then what did we study afterwards? Open set, closed set, something like, right? That's what we will study here as well. In the general D metric, how do you define open and closed sets, right? Something like, and then how do you define continuous function? Same thing, exactly same fashions will be happening here as well. So what I mean is we try to generalize every stuff we have studied in real analysis on the real number line to this general metric space, right? The real number line we have studied, in the real analysis with distance, with absolute value thing is a kind of example of metric space here. And on that specific example of metric space, we have finished studying what? Open, closedness, continuous functions, something like everything, right? And then how do we develop that theory to what? More general metric space here. That's our task in this class, this semester. Yeah. And then what's next? After we study metric space, after we develop everything in the metric space, what's next?
Metric space.
Topological space. You have heard about the topological space, which is what? Which is the generalization of a metric space, right? Yeah, metric space is one example of topological space. And then on that topological space, again, how do you define open, closed, continuous functions, etc.? They are the steps in real kind of analysis, trending. And I don't know how much we can cover, but let's try anyway. Yeah, let's try anyway. Try to cover as much as possible this semester.